Back in exercise physiology, you more than likely talked about bioenergetics. These ideas of how do we take food stuff that we consume at meals and turn it into energy to use for exercise or daily living. So, because of that, I'm going to just give a quick overview, a quick review of bioenergetics, bring us back up to date, make sure we have all the gaps filled in, and so that we're ready to move forward. So, when we talk about bioenergetics, one of the key things that comes up a lot is this idea of enzymes. Now, enzymes are these chemicals that basically speed up a reaction. Now, one of the quickest ways to spot an enzyme is if a word ends with ACE. A-S-E. There's things like reductase, hydrogenase, lipase. Anytime you see ACE, it's an enzyme, and usually the word before it tells you exactly what it does. For example, lipase breaks down lipids. But to picture what this looks like, let's look at this graph here. Basically, we're going to speed up a reaction by decreasing the energy needed to activate a reaction. So if any reaction, you have to put in energy to start it with the hopes that you'll get more energy out on the tail end. But basically what happens here is the energy supplied without an enzyme would be way up here. So it's going to take a lot of energy. So when you have chemicals sitting inside your body, and without an enzyme, they stay up here. They still happen, but the energy it takes to get over that hurdle is much higher. So it happens at a slower rate or just a trickle. Now, if we add an enzyme to the picture, it decreases the barrier, it lowers the hurdle. So now, because the hurdle is lower, it's being jumped more and more and more often. So to give you an idea of this, let's use lipase. If there is a lipids present and there's no lipase, then the lipids would still be broken down. But once lipase is there, they're getting broken down more and more and more. So then what happens is we take these reactants, the things that go into the chemical process, and then we take the products at the tail end. Now, one of the interesting things we'll see is with enzymes, a lot of times these end products will come back full circle. And if we start to have the end products build up too rapidly for certain processes, then they will cut off the enzyme that is triggering the process in the beginning. So because of this, once you have an enzyme present, the enzyme only continues to exist in high concentrations when it's needed. If you start to get what you want out of the tail end and that's starting to build up, then the process will loop back and cut off, which is a really cool factor because otherwise we'd always be going. All these processes would be spiraling, snowballing out of control, but instead we have these cutoff valves. So here's what that's going to look like, right? So let's take a general feel. This is not anything specific. This is just an example of a chemical reaction. So you have energy that goes in, the enzymes there, the fuel goes from inactive to active, and then we're producing energy. We have a byproduct. We have another enzyme that's creating another byproduct, and then we have another byproduct. So all these enzymes are working together. So we have enzyme 1, 2, and 3, and we're going down the process. Now what you'll see here is you have this term rate limiting right here. Now what this means is this particular enzyme is determining the rate at which we start the process. So if this enzyme is not present, then we're sort of stuck right here. We won't continue. But if there is this enzyme, it's going to go all the way down this product and it's just going to take off. Now, what happens again is this byproduct through negative feedback is going to go back to enzyme 1, that rate limiting enzyme, and shut down the process. By shutting down the process, then none of this is produced and we slow down. Because we aren't trying to always produce energy. We're trying to always produce the right amount of energy. And that's what this is all about. So you'll see these rate limiting enzymes, and you may remember them from before. So there's different factors that are going to alter enzyme activity. So if you think about what happens in your body once you start exercising, for example, it's going to often be things that are going to trigger enzyme activity. So, what I mean by this is if you get up right now and you run out of the room and you just keep running and you keep running and you run for 20 minutes, and then you think about what that would look like. You're probably sweating. You're probably maybe a little bit more tired, a little bit more sore. Depending on the activity that you're doing, you might have started to produce lactic acid. So what this is signaling is your body temperature has risen during the activity. Now, because of the rise in temperature, you also have a rise in enzyme activity. So what this means is as you start to exercise, internally your body is reacting to the temperature by making the enzymes more efficient. So these enzymes are functioning easier in warm body temperatures than in cooler ones, which makes sense because when do you want the enzymes to work? Well, probably when you're producing body heat and when you are warmer. So it's a kind of a cool little system that's in place to help us. Additionally, pH, let's say you have your lactic acid being produced, you're really working hard, you really need things to be going full force because you're producing lactic acid. Well, the pH in your blood and your tissues is now going more acidic. And because of this change in pH, you'll see shifts in enzyme activity as well. All this is just to keep you kind of in homeostasis and create the environments that you want. So we have three macromolecules. You may have heard of this if you've dove into nutrition at all, but there's three main macromolecules, three main fuel sources. There's carbohydrates, fats, and proteins. Now, carbohydrates are our first one. They come in different forms. They come in mono, di, or polysaccharides, depending on how big these molecules are, with the monos being the smallest. And an example of a mono that we will see a lot of is glucose. Glucose is this liquid form of carbohydrates in our blood. It's the usable form for energetic systems, but it's a very simple sugar. Now, once you start to stack two monosaccharides together, you get other things. For example, we could take sucrose. Sucrose is one glucose and one fructose combined. And that's what table sugar is when you bake or when you add sugar to your coffee. What you're adding is this combination of one glucose and one fructose. Now, once we start to stack lots and lots of monosaccharides and disaccharides together into these big chains, what you have is things like glycogen or cellulose or starch. In foods, these are harder things to digest. But as far as glycogen goes, glycogen is the storage form of carbohydrates in the body. All throughout your muscle, and particularly around your liver, you're going to have glycogen. So what happens from energetic standpoints is the breakdown of glucose is called glycolysis. Anytime you see the lysis, L-Y-S-E or I-S, anytime you see those in science, that means the breakdown of something. So glycolysis is the breakdown of glyc, which is glucose, right? So the breakdown of carbohydrates into a fuel source. Glycogen, if we take it from storage form and we want to break it down into glucose so that we can use the glucose, that's called glycogenolysis. Again, you got that lysis for breakdown. And what are we breaking down? Glycogen. So we break down these big chains into smaller chains that we can then break down to create ATP, the energy currency of your body. Now, our next one is fats and lipids. Come in different forms. The main one I want to talk about here is triglycerides. So lipolysis, again, lysis of lipo meaning fats. So the breakdown of fats would take triglycerides, break those down into usable forms. The liquid form of fats in the body are going to be fatty acids. These are the usable forms for energy. You'll see those talked about later. but you have different things that are classified as lipids, including things like cholesterol or other steroids. Our next macromolecule is proteins. Now, proteins are built of amino acids. So if you take different amino acids and you piece them together, sort of like Legos or building blocks, you're going to create different proteins. But their smaller form is amino acids. Now, proteins are less commonly used as fuel. They're more of an emergency supply. In situations like starvation or when you have limited resources, that's when you would start to break down proteins. The reason for that is because proteins in themselves are very hard to metabolize. What you need to do is actually turn them into glucose. And the reason for this is because you're going to go through this process called gluconeogenesis. Genesis, just like in the Bible, is the beginning. So the beginning, neo means new, and glucose. So what are we doing? We're forming something new out of proteins, and that something new is glucose, right? So what we're going to have these amino acids and proteins do is be converted into glucose within the liver, and then glucose can then be utilized as a fuel source. And the other thing is amino acids are used as metabolic intermediates. You'll see different amino acids coming into play to kind of fuel these processes. Fuel is probably the wrong word. It's not a fuel, but rather a bridge in the process. It passes, it links things along, and continues these processes. So as promised, we have this primary energy currency within our body, and that's called ATP, or adenosine triphosphate. Now, ATP is formed in a pretty logical way. Adenosine triphosphate, so what do you think it is? Well, it's this 3 phosphates together. And we can break ATP down using ATPase. What's that? ACE enzyme. So the enzyme for ATP breaks it down into ADP and inorganic phosphate and energy. Now, what we have in great abundance within the body is this ADP. So because we're breaking ATP down into ADP, which is adenosine diphosphate, then we have this piece, these pieces. Now, if we add an inorganic phosphate to ADP, that's when we get ATP, right? Because diphosphate plus phosphate equals triphosphate. So in this case, we have energy production by breaking ATP down using ATPase into ADP, inorganic phosphate, and energy. So when people ask, okay, so if this is our primary energy source, we probably have a lot of it, right? Well, not exactly. We only have about 100 grams of ATP in our body at any given time, which is a problem, right? Because if you want to go exercise, you want to go run out the door right now, what are you going to need? You need energy, and you're going to burn through 100 grams relatively quickly. So we need to be able to continually build up and develop new ATP, and that's where these energetic systems come into place. So the formation of ATP can happen in different ways. You can go through the ATPase system. You can do glycolysis, glycogenolysis, both anaerobic and aerobic pathways. So you probably remember the ATP-PC system, the glycolysis system, the oxidative phosphorylation system as your 3 primary bioenergetic pathways. So let's talk anaerobic first. This is a scenario where you do not have oxygen. These are quick scenarios. You get up, you start moving, you haven't had time to breathe yet, to actually bring oxygen into the body. So you have this anaerobic system. First one's ATP-PC. This is where we take phosphocreatine that's laying around in our body, ADP that's laying around in our body, combining them using creatine kinase, again, an enzyme that creates this process. So when that enzyme starts being produced, well, guess what? The PC that's sitting there, the ADP that's sitting there combines, and the byproduct here is that we end up with ATP. Our other one here is glycolysis, which takes glucose in an anaerobic fashion, breaks it down to 2 pyruvic acids, or 2 lactic acids, depending on the scenario. But here's your ATP-PC. Again, ATPase breaks down ATP. It's ADP and phosphate and energy. But phosphocreatine can also be broken down into creatine and a phosphate group. We can put that phosphate up into, combine with the ADP and create more ATP. Our next one is glycolysis. Now this is always super busy and freaks people out when they're new to it, and that's okay. I understand. And the reality is, I've been studying this stuff for a long time, and I don't always remember every step in order, right? As far as what all these long names are, we can reference it, we can understand what they are, but there's probably some bigger concepts for you to grasp. And to do this, let's split it up into 3 phases. You have an investment phase, a split phase, and a production phase. Just like way back at the beginning, I'm going to skip back here where we showed this. What do we need? Well, we need an activation energy, and then we need a production. So that's what we're going to see here is an investment where you invest energy in. By investing that energy in, we then see the process split at a certain point. We go down 2 of the same process, essentially, where you see electron transport chain. Either side is doing the same thing, but we've kind of split in 2 now. And this is where we get our actual big production of energy. So we put energy in at the beginning. ATP goes in. And then we split. And then once we get to production, we see ATP out with this resulting pyruvate, which can be converted to lactic acid if we can't get rid of hydrogen ions. Don't worry about that quite yet. What I do want you to know is the rate-limiting enzyme. So if you remember back, the thing that's controlling whether this happens is phosphofructokinase, or PFK. So this step 3 here is what's stopping or starting the process. It's sort of like the valve. It can turn it high, it can turn it low based off how much PFK is present. But if PFK is there, everything else is going to happen. So like I said, pyruvate, if you don't get rid of this extra hydrogen ion, we have the NADH plus the H ends up in NAD. But the main idea here is pyruvate may enter the citric acid cycle, or you might have heard the Krebs cycle. Either name works. But if you're in an oxygen-poor environment, you aren't in an aerobic environment, then anaerobically, pyruvate isn't dissipated, isn't utilized, so it's converted into lactic acid. Lactic acid is something we can track to determine whether we're anaerobic or aerobic. Now, oxidative phosphorylation, so let's say those pyruvates are in an oxygen-rich environment. We're able to utilize them. We're using an aerobic system, so we spit out the end of glycolysis and we have pyruvate. Pyruvate can then go down through stage 1, and it creates what's called acetyl-CoA. And we can use other forms like amino acids or fatty acids or glycolysis. So we have all 3 macronutrients represented here. But at the end, they're going to spit out acetyl-CoA. Once we get to acetyl-CoA, this can go and be the key that starts up the Krebs cycle. And the Krebs cycle is this loop. You might have also heard it as the citric acid cycle because the first step is citrate. Either name works, but you would have the Krebs cycle. And what happens is as we spin around, we are spitting out different pieces, which then can go down the electron transport chain and be converted into ATP. So it produces energy. But these are the main ideas here. So to go look at this a little bit closer, your rate-limiting enzyme of the Krebs cycle is going to be isocitrate dehydrogenase. So it's the one that's controlling whether we spin around. If there's isocitrate dehydrogenase there, we're spinning. But if it's not there, then everything sort of slows down or starts to, just slows down. It doesn't completely halt really ever. Similarly, we can get fats. If we want to start this Krebs cycle, if we can get to acetyl-CoA, then we can start the cycle, right? So amino acids, you can take, go through gluconeogenesis to produce glucose, pyruvic acid, acetyl-CoA. But what you can also do is fats is a big energy source, particularly aerobically. We'll talk about that in a different video. But if you have these fatty acids can be broken down to acetyl-CoA through a process called beta oxidation. So if beta oxidation happens, we break down fatty acids into acetyl-CoA. We have this piece we need. That piece gets plugged into the Krebs cycle, and energy starts getting produced. So in this way, we end up with both fats and carbs and even amino acids or proteins being a useful fuel source. So at the end of the day, this is what it's going to look like. So if we have one glucose molecule, we're going to net 32 ATP. Historically, we've thought it was 38, but the reality is it's 32 because we're losing some, we're gaining some along this process. That's just details. But here's some of the main things to know. These are interesting things from a biochemical standpoint as far as what is triggering this process and what's keeping it going, what's stopping it. So we have our systems here. We have ATP-PC, glycolysis, Krebs cycle, electron transport chain. Each of these is a different step of energy production. Again, glycolysis can be aerobic or anaerobic. But you can see what your rate-limiting enzymes are. Creatine kinase, phosphofructokinase, isocitrate dehydrogenase, or cytochrome oxidase. But we can also see what's stimulating and inhibiting these systems. Now, what you'll see here is across the board, while we have some different pieces to each, we have similar strands as far as all of them are stimulated by ADP, because if you break down ATP, you end up with ADP. So if ADP is in high abundance, it means a bunch of ATP is being broken down, which means that you need more ATP so that you have energy. So you start up these processes, you go, and then all of a sudden your demands of your exercise or whatever you're doing is met. And then you have a bunch of ATP starting to build up. And you don't want to build up huge, massive stores of ATP. You need just enough to survive and get through the next step, the next step, the next step. So with all these ATP built up, that sends a signal back to the rate-limiting enzymes, and it inhibits these pathways. It shuts them down. And this way, we produce the appropriate amount of energy, not too much, not too little. And it's a really, really refined and really cool thing that is built into humans. So if we talk about these systems, we're going to be curious about the application, the aerobic versus anaerobic. So we can see this idea of an exercise that's 1 to 3 seconds is going to be almost 100% aerobic. One that's 120 minutes is going to be almost 100% aerobic. And we're really kind of that 50-50 mark, maybe 2 minutes and 45 seconds typically of an all-out exercise. What this does not mean is if you get up and you walk for 5 seconds, you don't have huge demands, right? So maybe that is a little bit more aerobic, but if these are some pretty intense 4-minute effort, 10-minute effort, 30-minute effort, 120-minute effort, then this is roughly the cutoff. So if we look to see what that translates to, we can picture this in the terms of sports. So a marathon, almost 100% aerobic. 100-meter dash, almost 100% anaerobic. Now, what I really want to stress to you is even though you have these systems, at any given time, the aerobic system is contributing to whatever you're doing, and the anaerobic system is contributing to what you're doing. Right now, I'm sitting here, and to some degree, ATP-PC is happening. To some degree, anaerobic's happening. But to the largest extent, aerobic is happening, right? So even if you're at a full sprint, you have some aerobic system going. So what I'm saying here is it's important to understand that it's not quite as clean cut as this shows. As far as, yes, this is the cutoffs and this is roughly where we're at, but the reality is everyone is using some form of every system. So there's probably a place, while let's say a boxer might do some aerobic training and some anaerobic training because they're roughly 50-50, even a marathoner probably occasionally needs to do some sprints. It could be helpful. Or maybe someone who's doing a 100-meter dash might want to go for a cool-down jog or something like that that's aerobic. Because to some extent, each of these systems is important for everyone. It just doesn't make sense for a 100-meter dash runner to go run 10 miles and expect to get better at the 100-meter dash. Their time would be better spent sprinting, because that's logical, right? Similarly, if you want to say, let's take football for an example. Every year you hear stories about a coach that during summer training had their football team go run 5 miles or something. And it absolutely killed the football players, right? Is a 5-mile run a good training for a football player? No, absolutely not. Not a good training method at all, because they aren't ever using their aerobic system, only just a little bit. So you don't need to be spending so much time on the aerobic system with a football player. So what should you be doing? Well, you should probably be doing some all-out sprints with big, long rest, giving time for, if we cut into the anaerobic system for 10 seconds, that we have time for all that fuel to be built back up, for the ATP to become available again so that you can burn through it real quick in a very short term. Because if you're going to train those systems, then train those systems. Don't mix, right? So that's the application here. If you have any questions, reach out to your instructor.